Hi everyone, my name is Satyaam Raha. Welcome back. So in this video, let us learn a very elegant concept in deep learning, which is dropout. So in the previous video, we have already seen overfitting is a very serious problem when it comes to deep neural network. Now the first approach, as seen in the last video, is using regularization, right? So we could either use L1 regularizer or L2 regularizer, just like we used in machine learning concepts. Now, coming to deep learning, there is a very elegant concept that is a dropout. Now, how does it work? So, just remember in random forest what we did. A random forest is basically a ensemble learning concept in machine learning. So, what it does is basically in normal decision trees, what happens if we grow a tree to a huge depth, it overfits, right? So in random forest, the concept is we'll not have a single decision tree, we'll have multiple decision trees now. Okay, it will be a random forest of trees. Now each of these trees in random forest has a very huge depth or fully grown decision trees. Okay, that is, it will go till the end of its depth. Fine. That is until it reaches the pure nodes, it will continuously go on increasing the depth, right? So each of these trees in the random forest is a fully grown tree, and that is why they will be overfitting. Each of these trees will be overfitting, right? Now what it does is each of these decision trees in a random forest sees a different set of features. Let us say I have, for example, I have 4 different features. Okay, F1, F2, F3, and F4. Now, let us say we have 2 decision trees in a random forest. Now, let us suppose the first decision tree is trained with only 2 features. Let us say F1 and F3. Okay, and the second decision tree sees the features F2 and F4. Okay, and let us say I have another decision tree. Let us say we use 3 decision trees in our random forest, and it sees let's say F1, F2, and F3. Okay, randomly. Okay, now what will happen? Each of these decision trees in the random forest has seen a different set of features. It might be overlapping, but it sees completely different set of features, right? Now what will happen? As a result of that, we have some kind of randomization because the features are chosen randomly, right? Now what will happen? Finally, we take the random, we take the majority vote out of it. Okay, let's say decision tree 1 says it's class 1. Let's say decision tree 2 says class 1, and decision tree 3 says class 0. So majority says class 1. That is why the final result of the random forest will be class 1, right? This is how the random forest actually works. Now what we did here, we actually used the concept of randomization with regularization, right? We simply used single decision trees which overfit, and then a bunch of those trees are used so that this particular overfitting gets cancelled, right? So can we use this concept in case of deep learning? So in that way, dropouts came into view. Okay, so we'll use the same concept when it comes to dropouts. Similar concept. Okay, now as you already know, that random forest is such an algorithm in machine learning which normally gives a very good result, very good accuracy, right, than decision trees. The reason is this. The reason is we have randomization with regularization to get regularization. Now let us see an example of how dropout works actually. So let us see. So let us say this is a neural network. Let's say so that I do not waste time, I have already drawn it. Let us say this is input layer, this is hidden layer 1, this is hidden layer 2, and this is the final output layer. Okay, so they are fully connected, right? So now what happens is, this particular thing, this particular neural network, what will happen in this neural network, it is a standard neural network which will overfit in normal scenario. Okay, this is a standard or normal neural network. Okay, which will normally overfit because of so much dense connections. We have already seen in the last video why deep learning models or deep neural networks actually overfit. Now in the concept of dropout, what we do is we randomly drop out certain neurons. Okay, we normally drop off or switch it off. Okay, this process basically mean these neurons are switched off in a particular iteration. Okay, randomly. These crosses are done randomly. I could have crossed up this one also. Okay, so in each iteration, randomly certain number of neurons will be dropped off. That is why the concept dropout. Okay, now what will happen? As a result, see, these connections will decrease, right? Here what will happen? We'll have these two connections. Here we'll have these two connections done. Here we'll have this connection, and this one, right? And from here we'll have this, this. Pardon my drawing capabilities. I'm very good at drawing. Okay, anyways, so look at this neural network now. This is after dropping out, after using dropout. Okay, after using dropout. Now what is happening? In each iteration, what is happening? Some of the neurons are switched off, so the number of connections are getting less. As a result, as we have seen in the last video, that number of connections, if we increase the number of layers and number of neurons, then overfitting also increases, right? So here what is happening? We are not exactly deleting the neurons. What we are doing is we are switching it off randomly at each iteration. Maybe in the first iteration this is the scenario, maybe in the next iteration, let us use a different color. In the next iteration, let's say I switch off this and this randomly. Maybe here I switch it off this one and this one randomly. In the next iteration, maybe this one and this one. Okay, so it is done entirely randomly. So the result will be much more better, which will have no overfit at all. Okay, or which will decrease the overfitting concept, right? So there is a concept of dropout rate. So dropout rate P lies between 0 to 1. Okay, this is basically a probability that P percentage of neurons will be inactive in a particular layer in a particular iteration, right? That is what P indicates. Let us say we have used here P equal to 50%, 0.5. So what is happening? See, out of the 5 neurons, 2 neurons are dropped off. Here also 2 neurons or 3 neurons are dropped off randomly in each iteration. Okay, remember, this is not permanent. In iteration 1, maybe these two neurons are switched off. Maybe in iteration 2, this will be switched on. Maybe some different neurons will be switched off. Okay, so that is why this randomization actually brings the regularization concept. Okay, so this is how you can understand the concept of dropout. Now what will happen during the training time? See, in training time, what is happening? We have a neuron, let's say, and from this neuron we'll have certain weights going out, right? We have certain weights, let's say W1, W2, W3. We'll have certain weights going on. Okay, and this particular let's say they are connected further with certain neurons. Now what will happen? This particular edge will be present during the training time with probability P, right? The probability, see, offing the neurons means basically deleting of the edge, right? So let us understand it like this. Let us make it very simple. So in a particular iteration, this particular age W1 was present with probability P, right? So that is happening during the training time. That means in iteration 1, maybe this particular age was not present. Okay, now what we do during the testing time or the prediction time? Now during the prediction time, what should we do? Because these three particular weights were all the weights present during the training time, it comes out that the answer is no, right? Maybe in iteration 1 weight 1 was not present at all, maybe in iteration 2 weight 2 was not present at all, right? So what do we do during the testing time? During the testing time, should we consider all these weights or not? So it comes out that all these edges will be present, all these neurons or the connectivity will be present during the testing time or the prediction time, always present. But now what will happen? This particular weight 1 will be present with a probability P, because this weight was present in a particular iteration with probability P, right? Let us say the probability was 10%, 0.1. Okay, let us say P equal to 0.1. So this particular age was present in an iteration with probability 0.1, means 0.1 time, okay, or 10% of the time during the iteration, during the training, this particular age was present. Okay, again I'll explain it. It is a bit complex, but bear with me. See, what do I mean by W1 into P, W2 into P? This is during the testing phase. Okay, this is what we should do. Now, why is that relevant? See, P equal to 10 means 0.1 means basically 10%, right? Probability is 10%. So this particular age, that is W1, was present during the training time 10% of the times, isn't it? Right? 10% of the times it was present, or 10% of the times it was not present. Either way, you get the same result, right? We are simply weighting it. Okay. Similarly, W3, this particular age was present or was not present in the training time 10% of the times. That is why we multiply it with P, just to make it balanced. Okay, it's kind of a average kind of a thing. Now this P is basically a hyperparameter, right? So this is the concept of dropout, and you can play around with the value of P to see the optimal result. Okay, if P is very much high, now what will happen? If P is very much high, then many neurons will be switched off, right? And what will happen as a result? Will normally underfit, or will tend to underfit, because not many neurons are being used during training. And if P is very less, now what will happen? All the neurons will be present, almost all the neurons will be present, now will tend to overfit. So this P is nothing but a hyperparameter. We can do hyperparameter tuning to get the best value of P. Okay, so I hope the concept of this particular dropout concept is clear. If you have any questions regarding dropout, please let me know in the comment section. And if this video was any way helpful, please do share with your friends. Thank you for watching. See you in the next video. Bye.